Hello, class. Okay, today I'm going to explain chapter 6, energy and oscillation. And as before explain this one, is you have exam next week, and yes, exam one. As I mentioned, the exam will be online on the lockdown browser and responders monitor. And so actually, yeah. I also you may allow you allowed to use you will be allowed to use the formula sheet, and then I uploaded the D2L. Okay, let me show D2L. Where's D2L? It's D2L. Not this one. This one. D2L is you go to content, and here is I on the review for exam one. You can practice with these questions. And also for multiple choice questions, you need to practice with the multiple choice questions given in your homework assignments. And the other thing is also that is if you go to there and review for exam one, or there is also a summary one. This you can download this print. Then you can use this formula during the exam. Maybe you can add some notes there, because if you need to familiarize this one also. If you need some notes, but don't write the whole solution there. Yes. Okay, you have to print and you use this formula sheet to take exam during the yeah. That's okay. The other thing is that's all about exam. Now gonna the last time we learned the circular motion and the planets and gravity. Sometimes chapter 5 we studied. What's the exact title? Circular motion, the planets and gravity. I will give show some exercise questions, how to solve some exercise questions. It's chapter 5. Chapter 5. Let's solve some questions, how to solve. Maybe I already put there on the E11, EA. Maybe I'm gonna show some 3 questions how to solve it. check macro here. Next to chapter 5. E2, E5, E11, E14, E2, E5. I'm I'm copying the questions from macro here. E5, E8. I guess E8, E11 is the exam. Okay, let me share the slide. E2, E2. This is This is chapter 5 questions. Chapter 5 questions. This is homework question. Chapter 5. Chapter 5. That's the part of a review for previous class. And chapter 5.2 is a car rounds the curve with the radius of 40 meter at a speed of 18 meter per second. What's the centripetal acceleration of the car? We need to find the car is maybe it's running and along this circular path. Its radius is about r equal to 40 meter. 40 meter, and its speed is 18 meter per second. 18 meter per second. That we need by the centripetal acceleration. Centripetal acceleration is centripetal acceleration. You AC. What is AC? You can see here in the, I think maybe Bob says D to L. D to L is here is centripetal acceleration AC equal to, you can see here is AC equal to V square over R. How to find the centripetal acceleration? Okay. Centripetal acceleration, if we go to here, it's AC equal to V square over R. This is AC equal to V square over R. Centripetal acceleration. And then I'm going to come back to our slide. Yeah, this we need to find the AC. The AC equal to, in the formula, AC equal to V square over R. The V is speed of the car, 18 squared, divided by radius is 40. This will be, once you calculate this one, it can be 8.1 meter per second squared. 8.1 meter per second squared, because it is acceleration, its unit is meter per second. The next question, E5. Mass 0.35 kilogram. The ball moving in a circle. The end of string. This is like this. The string. This is rotating. Like rotating. It's the centripetal acceleration is AC is given there, 5 meter per second squared. What's the magnitude of the centripetal force? We need to find the centripetal force. We don't know my radius, but it's centripetal. Centripetal force is Newton's second law. You can see Newton's second law of motion is you can see F net force equal to ma. But in this case, acceleration will be A equal to AC. Then net force is only there is this tension force. Tension force can be that produces centripetal force, the FC. That is equal to tension force, also F net force. Then we can write FC equal to M times AC. M is mass of the ball. Ball is 0.535 kilogram times acceleration is 5 meter per second square. Then this will be 1.75 Newton. Unit of force is centripetal force. Force is just Newton. That is 1.75 Newton. This is the answer of this question. The other one is gonna see some review for exam. Maybe here. Review for exam. I think we can. Let me check there. Review for exam. Ferris here. We can see Ferris here. A carnival has a radius of 8 meters. Ferris here is like this rotating around here. The circle is should grow. And then here's center space here. Radius is r. R equal to 8 meter. 8 meter. Radius r equal to 8 meter. 8 meter. And turns so that the speed of riders is v equal to 4.5 meter per second. Question A. What is the magnitude of centripetal acceleration of the riders? Centripetal acceleration is simple. Just we need to find the AC. Just to use formula as before we did. AC equal to V square over R. The V is A square 4.5. This will be once you calculate this one is 2.53 No, hold on. This is, hold on. This is, yeah. Velocity is 4.5, speed 4.5, radius are a. Yeah, that is, once you calculate this one is about 2.253 meter per second squared. Meter per second squared. This is the answer for question A. Next one is question B. What's the magnitude of net force required to produce this centripetal acceleration for a rider with the mass given there, 75 kilograms? Exactly the same one. We need to find the centripetal force. Centripetal force is just mass times centripetal acceleration, right? This one. This is formula. Yeah, this is Newton's second law. You can see the formula sheet there. I guess centripetal force. Yeah, centripetal force is MAC here. MAC. This is centripetal force. Centripetal force is any force or combination of forces that acts on a body to produce the centripetal acceleration, including friction, normal forces, tension in a string, or gravity. The net force is related to the centripetal acceleration by Newton's second law. It will be Fc equal to MAC. Fc is centripetal force, M is mass of the object, AC is centripetal acceleration. All right, then can come back to the slide. Mass is 75 times centripetal acceleration, as we found 2.53. That this will be about 100. No, what is that? This is centripetal. This is centripetal force. This is exactly same to net force. Same to net force. Yeah. This is net force because there is only acting on the object is this net force is exactly same to centripetal force because the object is rotating. Yeah, rotating. So 75 times 2.53 will be 189.284 Newton. Newton. The other question is E11. Two masses are attracted by gravitational force. Two masses by attracted by gravitational force. The gravitational force is maybe this object is F12, F21. Maybe this object 1, 2, F12, 1, 2. Then the mass gravitational force is F12 equal to F21. Its magnitude is just maybe like magnitude is 9.6 Newton. It's this is action and reaction. That its magnitude their magnitude is the same, but directions are opposite each other. That is F12 vector equal to negative F21 vector, right? This magnitude exactly same magnitude, but direction is opposite. What will the force of attraction be if the distance between two masses is quadrupled? Quadrupled means that is distance is originally its distance is r, but this is later it became maybe 4 times. It becomes 4r. Then new force will be what will be maybe F maybe this force maybe we think just there. F what will be F maybe 1, 2. Sorry. Yes, of course. Newton's second law, Newton's the law of gravitation. Newton's law of gravitation. Gravitation. Is F equal to G m1 times m2 divided by r squared. This is the formula. The force is related proportional to the mass of individual objects, and also inverse proportional to the square of the distance. And here, let me show the formula sheet. I didn't write that. I guess the must wrote there. Hold on, how do I get this? Yeah, this one. What I wrote here, F equal to G equal to 6.67 times 10 to minus 11 power to, yeah, it doesn't matter. Yeah. Anyway, may use this formula. Then here's originally it was maybe F1 this guy is G, maybe F12, that's G, M1 times M2, R square is 9.6 Newton. 9.6 Newton. But now we're gonna find maybe new one, F new one, maybe F new F1, just one. What is F1? Maybe in this case, the G times mass doesn't change here, same object, but we change it only distance for R quadruple the square. This we can rewrite G M1 M2 equal to this. We can open this the power that's 16 R square. That this we can rewrite 1 over 16 G M R times M2 times R square. Right? Then we can say this is exactly this one, same, right? This F12 that 1 over 16 times F12, that will be 16, 2 times 9.6. That will be F1 equal to 0.6 Newton. This will be answer of the question. Magnitude of the 0.6. It factor the 16 times reduce the force. Yeah. We can originally was 9.6 Newton, but this 16 times reduced because distance, the quadruple distance bar, then this distance increased 4 times. That this will be increased. That the force is reduced, not increased, decreased. That's all. And now we're gonna see. Come back to chapter 6. Chapter 6 is about energy and harmonic oscillation. Energy and oscillation. Energy is important in our daily life. When you today we came to Lone Star College Creekside Center to conduct labs. And when you coming, you must the driver or maybe ride on car, and then the car has energy to bring you to the campus. Where the car get the energy. The energy is getting, if your car is a gasoline car, maybe burning gasoline inside the engine, that get burning energy, heat energy, thermal energy is converted to mechanical energy, which can run your car and operate your car. That also, if your car is maybe electric energy, maybe like Tesla, your car can be powered by electricity. Then electricity energy converted into mechanical energy to bring your car to the campus. Okay, this is about energy, and we're gonna learn these 5 sections: simple machines, work, important there is, and power, kinetic energy, potential energy, conservation of energy, yeah, springs and simple harmonic oscillations. They're gonna do pendulum lab maybe after next week, I guess. And here's the introduction. The quantity that remains constant and is conserved turns out to be what we now call energy. Energy did not play a role in Newton's theory of mechanics. Yeah, we didn't mention about energy when we studied Newton's laws of motion, but later people introduced about energy. It was not until the 19th century that energy and energy transformation were elevated to the central position that they now hold in our understanding of the physical world. This is here something bob is like random, but if starting here, this will be or the higher place, the I will be potential energy. But this will here is exactly low position. In this case, potential energy will zero. That it gained some velocity. Velocity means this has kinetic energy. This here is no speed. Speed is zero, but it's, kinetic energy is zero. Right? There is some kinetic energy gained here. But I'm gonna explain later this one. And here's a simple machines and work and power. Here's this guy's, Archimedes. Archimedes lever. He claimed, give me a place to stand on, and I move the earth. Crazy idea, but it's, I think theoretically he can do. Yeah, this is maybe Greek word. Mm, I think someone can. Is also no moi pa still, yeah, Kai, Tao, Yano. Yeah, this guy, if I have some mm, this kind of bar, he can move the earth. This is a kind of related simple machine. Okay. A simple machine is any mechanical device that multiplies the effect of an applied force, such as levers, pulley system, and inclined planes. If we here is a pretty big rock, you cannot lift by your ordinary force. But if you use this lever, then you can move this this rock with a small force. If you apply the small force, this length of the force, this arrow is small, but it's applied force here is really big. It's converted even, but in this case, you have to remember this move to displacement really long, but this displacement is short. That in this case, F1 D1 equal to F2 D2. Yeah. D2. But here is F2 will be F1 times D1 over D2. D2. That D2 is the D2 is big. Maybe okay. You have to apply the F1. F1 that I apply the force. F1 will be F2 D2 over D1. In this case, D1 is big. D1 is increased. Then D2 F1 will decrease. In this case, we can take advantage in force. We cannot take advantage in work, but we can take advantage in force. We just apply the small force, we can get big force. By applying a small force at one end of a lever, a larger force can be exerted on the rock at the opposite end. To move the rock a small distance, the other end of the lever must move through a larger distance. Yeah, larger distance. We need to move a larger distance. Yes, the larger distance, but here is short distance, just only moved by larger distance. But larger distance, instead, we can apply the small force. But this here is a small distance, but we can get really big force. In a pulley system, you can lift the weight a certain height by applying a force equal to only half the weight being lifted. This maybe think that this is heavy, about maybe 300 pounds. 300 pounds. 300 too heavy, maybe. I guess 140 pounds. 40 pounds is heavy. About maybe man's weight. A man, maybe, yeah. I think it will be heavier than mine. But for you pulling, just because this force is 140 pounds, but this can be separated, just distributed here. That is 70 pounds, 70 pounds, 70 pounds is splitted. And then 70 pounds, 140 pounds, this 140 pounds, the crates can be lifted by this lady. This lady also 70 pounds, also she only pulling on 70 pounds, with 70 pounds. And here is you can see here is when she pulled this just only maybe lift up 1 meter lift up there. And that is this rope is like this one, that this if you think this rope moved 1 meter, 1 meter band. It means this rope can be shortened and just this one new length. This will be shortened about 1 meter times 1 times 2. She no, pull 2 meter, 2 meter. Yeah, that only this weight only moved 1 meter, but she need to pull 2 meter the rope. Yeah, that but she can use only small force, small force, just half force to lift the this crate. Then it's very similar. Here it's only distance is small, longer, but force short, small. But this is force is big, but the distance is short. This case is the force is big force, but the distance is short. But ship force is small force, but distance is longer. You must pull the rope twice the distance the weight is lifted. Weight is 1 meter, 1 meter lift up, but this she need to pull 2 meter rope. The quantity force times distance is conserved. This product is called work. For an ideal simple machine, work output, work input. This is work input, work input, work input. Input is in this case F1 D1 is work input, work input, input. In this case F2 D2 is work output, work output. The output and input must be same, right? That is kind of conservation right there. And the ratio of output force to the input force is called mechanical advantage. In this case, F1, this is input force is output force F2 over F1. F1 is that is mechanical advantage. Is oh, why is this F1? This is a mechanical advantage. F2 over mechanical advantage. But for the pulley case, she applied maybe 70 pounds, but the applied force is 140. That means 140 divided by 7, that will be 2. That is pulley system. 2 is mechanical advantage. Yeah. Mechanical advantage. But in this case, input force is maybe the 70 pounds times 2 meter, 2 meter. This is input work, input work, work input, work input, work input, input, but the input, not input, input, and work output is work output, output is 140 times 1 meter. That is 70 times 2 is 140, 140 times 1 is same. Work input and output must be same. Then definition of work. If the force and the distance moved are in the same direction, then work is applied force multiplied by the distance that the crate moves under the influence of this force. That work is force times distance. Force times this formula here. Work is just written as W equal F times D. Simple. F times D. Then also you have to remember work is a scalar quantity, but it's force is a scalar vector quantity and direction of same direction. Same direction. Important. The distance moved to same direction. Maybe this guy is applied 5 Newton. That this moved the distance maybe 3 meter. That the work can be 5 Newton times 3 meter. That will be 15 joule, 15 joule, 15 joule, 15 joule. Then unit of work is called the joule in SI. Unit of work is 1 joule. That's 1 Newton times meter. Force is perpendicular to the motion, such as the normal force or the gravitation force. Sorry, that's not gravitation. Gravitation force. Gravitation force. gravitational force. Gravitation. Gravitational force acting on the plate do not work. Then force and force applied gravitational force is and mg is like here. Then normal force is n is here. But displacement occurs this direction. Displacement occurs this direction maybe. This direction displacement occurs. Then in this case, n vector and g vector is perpendicular. N vector and mg d vector is perpendicular. Also mg vector. D vector. This then not working, not working, not working. That is also when you talk about the force, you must specify some force. If the force is force, then force don't work. Yeah. That when you just talk about force, then you have to specify work done by a force. What force? That can be gravitational force. Sometimes this pushing force. Sometimes a normal force. You have to specify what force worked. That is important. What force? Force is important. In this case, this pulling force work. This guy work, but it's a perpendicular component. This 40 Newton and 30 Newton does this work, but this is not working. Perpendicular force is this component doesn't work, but this work because its direction and the direction motion and the directional force are parallel, but this direction motion and direction force is perpendicular, doesn't work. The work done by a given force is the product of the component of the force along the line of motion of the object multiplied by the distance that the object moves under the influence of force. Right. So you have to decompose it. When you calculate the force, maybe. It's you apply the force here. This creates that you're pulling. This may be 5 Newton, but you moved this one is how much? Just some amount of distance, just 10 meter was moved. But in this case, you have to decompose this force into horizontal and vertical. Maybe horizontal component is 4 Newton, vertical component 3 Newton, and this because this is the horizontal component. This F equal to F horizontal vertical component F horizontal component. 1 Newton. This is 3 square plus 4 square equal to 5 square. This is Pythagorean theorem satisfied. And then in this case, work can be work is just only we have to consider horizontal component work, but this vertical component doesn't work. That work can be 4 times 10. It's 40 joule. But 3 Newton doesn't work. 3 Newton doesn't work. Because 3 Newton is perpendicular to the direction of motion. Motion is occur this direction, but this 3 Newton vertical is just 90 degrees, right? Perpendicular. This is not working, but this guy is horizontal component working. I'm gonna see some example question here. It's example 6.1 sample exercise. How much work? A crate is pulled a distance of 4 meters across the floor under the influence of 50 Newton force applied by a rope to the crate. What is the work done on the crate by the 50 Newton force? If the rope is horizontal, parallel to the floor, the rope pulls at the angle. Question A is horizontal case. We just pull horizontally. We pulled. In this case, only this component is contributed for working. F maybe equal to 50 Newton. This question A case. That move to this crate is how much? Just 4 meter, 4 meter. That, in this case, simply we can multiply 50 Newton times 4, that 200 joule work done by the force. Question B. The rope pulls at an angle to the floor so that the horizontal component of 50 Newton is 30 Newton. B. That is question B is like this kind of situation. The horizontal component is only 30 Newton. This work, but this not working. Yeah, working. Work sometimes can be noun, sometimes can be verb, but it's not working. This guy only work, right? Because as I mentioned, the vertical component doesn't work, only horizontal component work. Even we have to, this angled case, we have to decompose this one. Yeah, it's 130 Newton, it's 40 Newton, but this not working, only this guy work. That's why we can write work equal to work horizontal component times this displacement D. That 30 times 4 is 120 joule. Then you can two cases, A and B case, that B work is less than A work. A work is 50 times 4 is 200 Newton, 200 joule. But this work is only 30 times 4. Only this guy doesn't work. Only this guy is work 120 joule, right? Yeah, different. Even same force applied, but it depends on direction of force applied to the object. How is power related work? Power means you in your daily life you use term of power. Power is sometimes powerful. Powerful means in physics we can define this way. Power is the rate of doing work. Rate of doing how much work per unit time. Yeah, per unit time. How fast work. And that powerful case of how best work. Okay, even same amount of work there that you need to do work, but some guys can really best to do that case of really high power, but some guys really slowly, that's less power. It is bound by divided by the amount of work done by the time required. That the formula is power equal to work divided by time. This work divided by time. Units of power is 1 watt, is 1 joule per second. Watt is just, I think, British physicist, then 1 joule per second. But also, a familiar unit is how horsepower. 1 horsepower is your car's horsepower or something. Horsepower means just horsepower is 746 watts. Is equal to 0.6746 kilowatt. The faster work is done, the greater the power, right? This is obvious. The faster work is done, the greater the power. What I explained just even some amount of work, they are same amount, but some guy is really fast to do, but some guy is really slow. There's less power. Some guy is fast to working. That this guy is powerful. And the next section is about kinetic energy. I think the work is just work here. Work means just we moved some object from one place to another place. This force is applied, then we move the D. That's work is F times D. Simple. But energy is generally, as I mentioned, energy. This textbook didn't define, but energy is kind of I think maybe ability to work. Yeah. Just how much work. In this case, if you have something object is running, just maybe, I guess maybe rock. You throw rock, there is a crate there that hit maybe some box. Then this box can move. That means this guy can work, and this guy has energy. Then ability to work. This guy has work. Then energy associated with the motion of object is called kinetic energy. Motion of object is it's related. If some object has velocity moving, in that case it has kinetic energy. Originally it was speed 0, but I pushed with force F, that this moved here, that it gained some velocity V. That its kinetic energy is equal to 1/2 times mass times velocity squared. This is formula. Definition kinetic energy equal to 1/2 the mass of the object times the square of its speed. Work done is changing kinetic energy. This is called work energy theorem. Work energy theorem. Energy theorem. Work done. That's the work done means work is just changing kinetic energy. Changing kinetic energy means final kinetic energy minus initial kinetic energy. As I mentioned, delta is change in a quantity. Change in a quantity, in a quantity. That's delta is F minus I, the final minus initial. Final kinetic energy minus initial kinetic energy. Final kinetic energy minus initial kinetic energy. Initial kinetic energy. This is work energy theory. Obviously, if I do some work, this guy work, that's if I apply the force that this guy moved to, then this guy the work, then the work, then this create gained energy that kinetic energy changing kinetic energy. As I mentioned, initial kinetic energy minus final kinetic energy can be the work. Just it means in this case we can see. This is initial kinetic energy, final kinetic energy, then 1/2 mv square minus 0 equal to F times D, right? This is work. This is change in kinetic energy, change in kinetic energy. We're gonna solve one problem. Starting from rest on a frictionless floor, you move a 120 kilogram crate by applying net force of 96 Newton for a time of 4 seconds. This results in a final speed of 3.2 meter per second. After the crate moves the distance 6.4. As I mentioned, here is a crate here. I applied force, F applied, then this moved here. How much? The distance D. That this initial velocity is V naught equal to 0. Final velocity is maybe 3.2 meter per second. Let's gain some velocity, right? In this case, first question is work done on the crate. Work is just force times displacement. Force times displacement. Force times work is the formula. Because formula is force times displacement. Force is 96 Newton. Displacement is 6.4 meter. Distance moved distance is 6.4 meter. Then 96 times 6.4 is 614 joule. This is work. Question B is the final kinetic energy of the crate. Its mass is 120 kilogram. The final speed is 3.2 meter per second. Then we can kinetic energy is 1/2 times mv square. Formula that we can find 614 joule. This and this is same. Why? Because that is what I explained. The work equal to changing kinetic energy. Change, that means final kinetic energy minus initial kinetic energy. Final kinetic energy is, as we calculated, 614 joule minus 0. Initial kinetic energy is 0. But it's work. Work is 614 joule. Right, what I explained, that this means exactly same to delta K is 614 joule. Right? This is work energy theorem. Work energy theorem. That's proved. What's negative force? the frictional force exerted on a car acts in opposite direction. Frictional force is opposite direction, like this one. It's opposite direction. Yeah. The moving direction of motion is here, but its force is opposite direction force. In this case, we can think this is negative force. Direction of motion, and is this front there, but the force is opposite case. You can see that's negative sign there. That is negative work. This is negative work. Negative work. Because of this friction, maybe this guy is a brake, maybe I think this guy step a brake, and then this initial some velocity that will be stopped. There's maybe red light there that this stopped. Then how much you work with originally work with something there, maybe 100 joule, 1,000 joule, but final original kinetic energy 1,000 joule, but final kinetic energy will be zero because kinetic energy is equal 1 over 2 mv square, but v is that is zero, that this kinetic energy must be zero. Then changing kinetic energy, this is initial one, this is final one, delta k equal to kf minus ki. This is 0 minus 1,000 joule. That will be negative 1,000 joule. That means negative change in kinetic energy. It's exactly the same to the work done by the frictional force. That is a negative one. Yeah. The work done on the car by the force is negative work, removing energy from the system rather than increasing its energy. For a frictional force of magnitude F, the work done is W equal to negative F times D. Yeah, this is negative. If the car moves a distance d while decelerating, stopping distance of moving car, the stopping distance of 60 miles per hour will be 4 times that required to at 30 miles per hour because the work is proportional to the distance. But this is 2 times. Why? Because its kinetic energy is 2 times. Right? This is in this case 1 over 2 mv square. V square. That is the delta v is delta k. Delta k is a work. That is fd. But maybe delta k is negative. Maybe negative fd. F friction d. That this is 0 minus. This is final kinetic energy 0. Initial kinetic energy 1 over 2 mv squared equal to negative fd. That this will be same to 1 over 2 mv squared equal to fd. That this is stopping distance. This is speed, original speed before stopping. That if we increase twice, that will be twice squared. That will be 4 times. Yeah, we need to increase the stopping distance. Yeah. That's why we should not speed car. Yeah, that's very dangerous. Even you find some object there that people hitting, you have to stop. But the stopping distance, if you run maybe 30 miles per hour, case maybe you can get maybe 2 meters. But if you run 60 miles per hour, it'll be 4 times increase that 8 meters. Yeah, stopping distance. Now I want to explain about potential energy. Gravitational potential energy is one important potential energy related to is associated to something position. Potential energy associated with position. If this the lady is putting some this heavy box here, that this is really high place, that if she drop this box, she can crack the coconut. That means she can work because this box has some energy. That if you have energy, you can work. Morning time, if you have breakfast, then you gain some energy, then you can work, maybe go outside to do some work. Also you can study is also kind of work. And the work done by the lifting force increases the gravitational potential energy. Potential is maybe high place this high energy, high potential is low place potential is the gravitational potential energy is equal to the work done by the gravitational force. You work done, yeah, you lifting this work. What is work here when you lifting up when potential energy 3.2, 6.2, 3. You pulling this box, yeah, box maybe by using some rope here. It's pulling. That this you move to about 1 meter, maybe h. That you apply the force is F. That it's gravity is mg. That it is moving maybe constant velocity. In this case, F force and mg is the same. F equal to mg equal to 0. Newton's force law. Newton's force law. Force law. That in this case, F equal to mg. Then what is your work? Then you move to h, move to there. That your work is W equal to F times h. That means h F equal to mg. That mg times h. This is work done by the pulling force, lifting force, lifting force, lifting what force, the force lifting the cradle. This is exactly the same to the potential energy. Potential energy equal to just mgh. Mass times g is acceleration due to gravity, 9.8 meter per second squared. This is potential energy equal to potential energy. Potential energy. Where we use the abbreviation potential energy to represent the potential energy, and weight of the crater is mg, and the height of the crater moved h. The mgh is potential energy. The essence of potential energy, the term potential energy implies storing energy to use later for other purposes. You can store energy here, then you can crack. You can use this energy to crack the coconut right here. Potential energy involves changing the position of the object that is being acted on by a specific person. For example, in this case, gravitational force, right? But it's not only gravitational force, but also there is another force, elastic potential energy. Force is gravitational force here. I'm gonna write here is a crate with a mass of 100 kilogram of is lifted. 100 kilogram lifted. This mass is 100 kilogram, and the dock above ground lifted onto a loading dock 2 meter. H equal to 2 meter. How much potential energy has been gained? P equal to mgh. We can write this. M is mass is 100 kilogram. G is acceleration due to gravity, 9.8 meter per second square. H height is 2 meter. That is, if we calculate 1,916 joule of energy. If you move the box, original was here, but you moved this 100 meter, 100, just 2 meter moved up, then this gained PE equal to 1960 joule. And this P equal to 0. Originally was initial, this is binary, this initial is 0. Right. Now I'm going to explain about elastic potential energy. Elastic potential is another form of energy. Work is done by applied force against an opposing elastic force, a force that result from stretching or compressing of object. Elastic potential energy. Elastic potential energy. If you have, here is maybe originally it's just equilibrium. This is like that, not stretched, neither stretched nor compressed. Then I apply the force. This is stretched, like stretched. How much? Just X stretched. It's K is called, that is string constant. K is spring constant. Spring constant is a kind of stiffness. Spring constant. Spring constant, then if it depends on force F equal to negative kx. If we moved there, that this force will be F equal to negative kx. How much stretch that force big? If we x increase, F is also a big force, right? Big force. You have to apply the big force. This maybe this force applied there. Then this is called Hooke's law. Hooke's law. Hooke's law. Hooke's law. Hooke's law. K is unit is Newton per meter. We're gonna do this one is when we harmonic oscillator later. We're gonna do spring harmonic oscillation and spring. Then here is spring elastic potential. If we stretch this one, that if I release this can come back, that it gains some velocity, it gains some kinetic energy, right? It means this has some energy there. This kind of energy is some energy stored here. This kind of energy called elastic potential energy. Elastic potential energy. Elastic potential energy. The elastic potential energy is depends on spring constant and the how much stretched or how much compressed. That elastic potential energy equal to 1/2 kx squared. There, it's not linear. It depends on scale of the how much this stretched, how much stretched or how much compressed. K is spring constant. Then Hooke's law, the spring constant K describes the stiffness of the spring. The force exerted by the spring is given by the spring constant multiplied by the distance stretched, or F equal to negative Kx. X is the distance spring is stretched. How much is this? Maybe this is equilibrium. Equilibrium is neither compressed or stretched. That how much you stretch it. Then here is the distance will be here x, that the force is like here, that, and this area will be work done by pulling force. This area equal to the area is this triangle area. I guess you can how to get this one. This area is like F force is applied here. that x is that's proportional. F equal to kx. This Hooke's law, because of Hooke's law, this is proportional, just linear line. Then if you length x, then we need to find this area. Area, what is this area? And this is a triangle. This is height is kx, f equal to kx. And then you can find this area is 1 over 2. Base is x times height is this height is kx. This will be 1 over 2 kx squared. This is work, or this is potential energy stored the spring. Elastic potential energy. And what about conservative forces? And forces such as gravity or elastic forces that lead to potential energy relationships are referred to as conservative forces. Conservative forces. Then gravity and elastic forces we call it conservative forces. Conservative forces. When work is done against the conservative forces, the energy gained by the system is completely recoverable for use in other forms of energy. You know, if I bring maybe if I bring this block, maybe this block here, in this case, it gained some kinetic energy, not this potential energy there. Potential energy. Then if I release there, this can go here, that is potential energy is zero. Potential energy, maybe H like that. This is potential H gained, but this potential energy, instead it's this potential energy converted to something velocity. That means this is kinetic energy. K equal to 1 over 2 mv squared. But in this case, initial velocity zero, that means kinetic energy is zero. Right? That means mg and mg plus potential energy plus kinetic energy is constant. It doesn't change at all. And if there is no friction there, let me show something like, let me show something passive later. Here we can see chart. If this boy is here, in this case we can see. Let me show you. Like at this case, potential energy is big, but its kinetic is small, tiny, because his speed is small, slow. But if I here at sorry, no, maybe slow, just and going to here, you know, here I gotta stop. At this case, potential energy is zero because its height is small, but its speed really fast. That kinetic energy is big. But total sum of kinetic and potential energy, it doesn't change at all. That's total. It doesn't change while moving. But here is this guy is moving up. There's potential energy increase. The kinetic energy just shrink. If he moved something like exactly top point, kinetic energy becomes zero because he just momentarily stopped, but potential energy will be big. This total energy will be only potential energy. Potential plus kinetic energy should be conserved. But if he moved like that, there, if he come here, exactly potential energy zero. That is exactly because height is zero. but kinetic energy maximum. It's speed really fast. Like total is it doesn't change. This is kind of energy conservation. You can do, yeah. This is in a best simulator. Here's exactly similar situation. Energy changes in a swing of a pendulum. Work is done on the ball by your hand. Is if you bring the ball is a little high place, then release. Then this work increases potential energy of the ball. Gravitational potential energy is mgh. When you release the ball, like the ball is top point, in that case, initial kinetic energy will be zero. Kinetic energy is zero. Biggest kinetic energy ball is gained here. In this case, kinetic energy will be speed is up that 1 over 2 mv squared. That potential energy at this case zero, right? Potential begins to change to kinetic energy as the ball begins its swing. At the bottom of the swing, potential energy becomes zero. Kinetic energy reaches its maximum value. That's, yeah, because its speed is maximum here. Pretty fastest speed. The ball continues to move to a point opposite the release point without stopping, and then move here. At here, it gained the height that potential energy, but its kinetic energy will be zero, right? Because it stopped momentarily. Stop means its velocity is zero, right? The ball continues to move to point opposite the release point without stopping. During this part of the swing, the kinetic energy decreases and the potential energy increases until it reaches the point where the kinetic energy is zero and the potential energy is equal to its initial value before release. And this is conservation of energy, as I mentioned, when only conservative forces. There is no friction, air resistance. Yeah, those guys not conservative forces. When only conservative forces are involved, the total mechanical energy of the system, the sum of kinetic energy and potential energy, remains constant. In symbols, the statement takes this form: if W equal to 0, E equal to PE, potential energy plus kinetic energy was constant, where E is the symbol commonly used to represent the total energy. That was what I showed in energy park. Of the three forces acting on the ball, only the forces of air resistance does work on the system to change its total energy. And the tension does not work because tension force is here. The motion is this direction, the perpendicular. The direction of motion, the V and tension is perpendicular. Work done by tension is zero, right? The tension does not work, and the work done by the gravity is already included in the potential energy. I'm gonna watch this, show this video.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to the point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it should not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at zero speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it zero speed, then this will be my last lecture. I will close my eyes. I don't want to see this. Please be very quiet. Almost didn't sleep all night. 3, PHYS1405. Physics works, and I'm still alive. See you Wednesday.
Okay, that is that's not the sound.
I am such a strong believer
It's just stop,
of
stop. Okay. The next one is a swing of a pendulum. Then we're gonna solve this problem. I just watch video tutor and macro here there. I guess show macro here.
Let's look in more detail at the pendulum example shown in example box 6.4. For a pendulum, there is a constant conversion of potential energy to kinetic energy and back to potential energy, with the sum always staying the same. At the point where the pendulum starts, the velocity is equal to zero, so the kinetic energy is equal to zero, and all the energy is potential energy. At the bottom, the height is equal to zero, so our potential energy is equal to zero, so all the energy is kinetic energy. At any intermediate point, there is both kinetic energy plus potential energy. And regardless of where we are in the swing, the total energy is always the same. In this example, the bob has a mass of 0.5 kilograms, starts at a height of 12 centimeters, and thus has a maximum speed at the bottom of 1.53 meters per second. Details in example box 6.4. Now let's look at something more interesting. At what height is the velocity half the maximum velocity? In other words, what is h when v is equal to 0.765 meters per second? If we know our velocity, we can find our kinetic energy by plugging in the mass and the velocity squared, and we get 0.147 joules. Now remember that the total energy is conserved. It always stays the same. In example box 6.4, we found that our kinetic energy plus potential energy was 0.588 joules. So, at any point in the swing, the sum of kinetic plus potential energy must equal 0.588 joules. If we know the kinetic energy is 0.147 joules, then our potential energy is just our total energy minus our kinetic energy, and we get 0.441 joules. That's the potential energy, but the question is, what is the height? Well, we know potential energy is mgh. So if we solve that equation for h equals p divided by mg, and we get 0.09 meters. We can convert that to centimeters by multiplying by 100. The height of the ball is thus at 9 centimeters. Notice that although the velocity is half the maximum velocity, the height is not half the maximum height. This is because our potential energy is directly proportional to the height, but our kinetic energy is proportional to the square of the velocity. There are several points that you should remember about this. One is anywhere you know the kinetic energy, you can find the velocity. Anywhere you know the velocity, you can find the kinetic energy, assuming, of course, you know the mass. Likewise, anywhere you know the height, you can find the potential energy. And anywhere you know the potential energy, you can find the height. It's usually easier to find the total energy either at the top, where the kinetic energy is zero, so you just need to know the height, or at the bottom, where the potential energy is zero, so you just need to know the maximum velocity. Once you know the total energy anywhere, you know it everywhere, and you can find the potential energy or kinetic energy at any point if you know the other one. So try it. Determine the velocity when your height is 6 centimeters using these steps. If you know your height, you should be able to find your potential energy. Know your potential energy and your total energy, which is still 0.588 joules, you should be able to find your kinetic energy. Know your kinetic energy, you should be able to find the velocity. Don't forget the square root. You should end up with a velocity of 1.08 meters per second. Try it. Thank you.
All right. And this is about the question, and I think this you need to watch the video. I think this is also a recorded video. Yeah, watch video. I think if you go to macro here, macro is macro. If you go to here, is I guess there's there's a video. Video is removed there. Is this? Yeah. You have to watch this video. Yeah, I think time is not enough to show them. This is macro here. You go to chapter the ebook. There is here's a chapter the 6.4 conservation of energy. You scroll down, you can get the video how to solve this problem. I don't need to explain this one. Yeah, you can watch this video. Your home, and the next one I'm gonna move to oscillation. Yeah. Last section is this last section is springs and simple harmonic motion. Oscillation of mass attached to a spring doing work or to pull the mass against the opposing forces of the spring increase the potential energy of spring mass system. If you are pulling there, that in this case potential energy increases. Potential energy increasing. You pulling this direction. But if you release, then here is a potential energy is decreasing. In this case, potential is exactly zero, but it gained some speed. This is kinetic energy, right? 1/2 mv scale. But this is also keep going there, that compress there. In this case, potential energy really increases 1/2 kx square, but kinetic energy is zero. That this also bounce back is like this can work, move back and forth. Yeah, this is called kind of oscillation. Once the mass is released, potential energy is converted to kinetic energy. The energy of a system changes continuously from potential energy to kinetic energy and back again. If frictionless effects can be ignored, frictional effect can be ignored, the total energy system remains constant while the mass oscillates back and forth. Plotting the position of mass against the time, the resulting curve is expressed harmonic oscillation, harmonic function. The motion is called harmonic motion. This is, if I draw this position is like moving like wow, back and forth, but time is blowing this direction, that this will be shown like this case. Yeah, this position is moving between here and here. This is called A amplitude. This is negative A amplitude is moving back and forth, is moving like that. This is maybe like, let me show some best simulator. Is as something spring. Let me show. Let me show this is best simulator. Do you think maybe have some weight? No, wait, this oscillation cannot show there. Okay, not this one. Hold on. I guess maybe this is better than that. This energy chart. If I hook this one is this can oscillate, right? Oscillate. If there is no L resistance, damping is zero. Maybe I pull that. That is maybe as you see here is potential energy. You can left side. Here is chart. Here is kinetic energy, potential energy of gravity. This elastic potential energy. If I pull that elastic potential energy increased by gravitational potential energy decrease. If I bring here, there is pull elastic potential energy increase the elastic potential energy. The kinetic energy is zero, right? Because it's not moving. If I release there, yes, kinetic energy sometimes increase like this. All the total energy is the conserved, right? This oscillation, this is kind of oscillation. Keep oscillating. Yeah. If we draw maybe, what is it? Maybe is there any ruler? Maybe graph there. There's no graph there. Okay, so should have some. Yeah, this is keep oscillating. This kind of thing is called oscillation. Yeah. Then the oscillation height, up and down is between negative A and positive A. This A is called amplitude. Amplitude is the maximum distance from the equilibrium point. Equilibrium point means neither compressed, neither stretched, neither compressed nor stretched, nor stretched. Yeah, position. Yeah. It's a spring line. Yeah, that the position is called equilibrium. This is here is equilibrium. We think maybe spring is right. That is original was that this guy is moving up and down is moving. Yeah, actually the object is moving up and down. Just oscillate between here. And here is also period. The T is the repeat time or the time taken for one complete cycle. Is this path is up and down, come back. This is one period of time. Yeah, time. This is period. Also, the reciprocal of the period is called frequency. Its unit is 1 hertz. Then number of cycles per unit time once. Yeah, that is f t equal to 1/2 over t. The unit of frequency is 1 hertz, 1 second inverse. Yeah. Amplitude is maximum distance. We study this one. I want to solve the question. One question. Okay. 500 gram of mass upon 5 undergoing simple harmonic motion at the end of spring with the spring constant K equal to 800 Newton per meter. And then its mass is 0.5 kilogram. The speed of mass is V equal to 12 meter per second. When it passes through equilibrium. 6.18 is what is 6.18? 6.18. That's 6.18. Yeah, this kind of it's a yeah. Spring is this block here, and spring is stretched, and then this can this is a original just equilibrium position, neither compressed nor stretched, and this originally it was moved x, moved here. That this is if we release this one, this can gain some velocity like that. But this will be compressed. This amount here is very compressed. Like that. What's the kinetic energy of the equilibrium point? kinetic energy, because originally the energy is stored. Energy conservation, you have to use energy conservation, but it's maybe speed is 12 meters per second given there. That's V equal to 12. That A is kinetic energy will be K equal to 1 over 2 KE. KE equal to 1 over 2 mv squared. 1 over 2 times mass is 0.5 times V is 12 squared. That is 100 both times. That is 72 times. That is 36 joule. How about does the mass travel from the equilibrium point before it turns around? How about does the mass travel from the equilibrium? This, what is x? And that means at that moment is kinetic energy will be zero. Kinetic energy zero, but is potential energy exactly same to the summation. We need to find x. That here is k kinetic energy plus potential energy should be constant. This is a constant. This is energy conservation. Energy conservation. That initially it's kinetic energy. Initially, it's maybe at this point kinetic energy. In this case, kinetic energy is 36 joule. Potential energy is 0. And this kinetic energy, potential energy, what is that? We can write that Ke equal to that's 36 plus 0 equal to 0 plus potential energy at point there. Yeah. Turning point. Yeah. This is exact 1 over 2 kx squared. We can find this x. X squared equal to 36 divided by k. That x is square root 36 over k. K is 800 Newton. Then 36 divided by 800 is we can find x will be 0.3 meter. 0.3 meter. This will be x equal to 30 centimeter. Exactly 30 centimeter. But this will be 30 centimeter. This is 30 centimeter. 30 centimeter. This is also 30 centimeter. This is also same 30 centimeter. X equal to 0. Maybe here exactly x equal to 0, but this x equal to 30 centimeter. This is positive or negative 30 centimeter. Okay, so will any restoring force produce simple harmonic motion? When mass attached to spring is moved to either side of equilibrium, up and down, as I shown, the spring exerts force that pulls or pushes mass back toward the center. Always, if we push it here, this case, this spring is pushing back. This is equilibrium position. Equilibrium position, but this force is pointing this. If we stretch the spring, in this case, the force also pulling back here. This force is this force also then this kind of force is called restoring force. We call such force the restoring force. In this case, it is the elastic force exerted by the spring. In any oscillation, there must be some such restoring force. For a simple pendulum, gravity is the restoring force. For small amplitude of swing, the simple pendulum displays simple harmonic motion. Right? This is a position like this. What I showed you. If I see, maybe if I show like not maybe again maybe if I see a simple pendulum. We think this. This is equilibrium position. This is moving like this one. This case maybe this moving back and forth like that. In this case, if I draw forces, gravity is like this one, and here's tension force. Then here is we think it's sum of force is like this one. This force is kind of F is just restoring force, restoring force, restoring force. If we think gravity can be decomposed into two components, one is this direction, another is this direction. This is maybe gravity, maybe perpendicular component. This is parallel component. Then parallel component will be work for restoring force, restoring force, restoring force. This point, this point position is equilibrium, equilibrium position, equilibrium position. That this force make this ball is back to this position, and then again this going this direction while going this direction, or is the strong force here, but eventually it arrived here. That's stop, and after stopping, then it will turn back to this direction. In this case, this force is also tension force is T. That gravity is, as I similar here is gravity here. mg can be decomposed into two components, like this is a W parallel component, another is a W perpendicular component. Perpendicular component balanced with tension force, that T equal to perpendicular, but this work for restoring force. This is gravity. W is weight and gravity, parallel component of parallel component gravity. This direction, yeah. Yes. Okay, maybe I hope you understand. Yeah. Yes. That's it. Maybe I hope you can take an exam well, and good luck on your exam. Bye. See you next Thursday.